Psalm 147, he, meaning God, determines the number of the stars and calls them each by name. And that certainly suggests a finite number of stars. Okay, some technical stuff from my astrophysics background. This is just basic astronomy, things that the astronomers have figured out over the last few hundred years. And we'd have various types of stars. And the most famous diagram is a Hertzsprung-Russell diagram, which has the brightness of the stars on the left axis, luminosity here, that can be an absolute or a relative term. And then there are several different scales for the horizontal axis. Temperature scale in this diagram, sometimes it is a color sequence or going from red on the right to blue-white on the left. But whatever, it's, or B minus V or something like that. There's various combinations of colors. But most stars follow along what is called a main sequence, from a small red star all the way through a medium-sized white star, which is our sun. It looks yellow to us, but that's because of the atmosphere scattering out the blue light. And then we got the very hot blue-white giants. And some of the name stars are mounted on here. There are some supergiants out there, and red giants and dwarfs. Dwarfs are usually considered sort of remnants of stars that have, to use the word, evolved off the main sequence. At least that's the theory. Okay, so down at the bottom, star type can usually be determined by examination of the color spectrum and the characteristic absorption and emission lines. And then once we know that, we can know where they are in this diagram, and then the star's standard brightness can be estimated. Like the sun has a luminosity here of 1, just to give it a relative scale. How far away are the stars? And here we have several different scales. The first scale is just using simple geometry, trigonometry, that the Earth is going around the sun, and so therefore a nearby star appears to wander back and forth in a circular orbit with respect to the distant stars in the background. And so we can measure an angle of parallax caused by the Earth's motion with respect to a nearby star, and figure out the geometry. Once we know the distance to the sun, then we can figure out the distance to the star. So this is very simple and gives fairly good measurements. The next thing is for farther out, we do have a Hyades cluster in the Taurus constellation, sort of a V shape of stars out there. And the distance is determined by the geometry of the historical drift towards the convergence point and the radial speeds. By matching those parameters, we can figure out how far away that cluster is located. Again, this basically geometry. Okay, well, once we know some clusters out there, then we can assume that all the stars in that cluster are roughly the same distance. And we got blue stars and white stars and red stars and a whole bunch of... So knowing a standard luminosity, we can start to work with distances to expect. So for an unknown, for a cluster at an unknown distance, by knowing the standard luminosity of the stars, we can figure out how far away the stars are located. Again, this is a fairly straightforward calculation, that the apparent brightness of the star decreases with the square of the distance to that star. You just take any light here on Earth, move it farther away, and it gets dimmer and dimmer with respect to the square of that distance to that location. And therefore, the distance to a star can be determined by measuring the dimming of the star and compare that to the expected luminosity from the star type. Okay, distances to nearby galaxies. What we use there for a scale are supernovae, novae, and certain variable stars, like Cepheid variables and so on. There's a bunch of others as well. And these variable stars have standard peak luminosities. In other words, when they get bright, they always get bright to a certain absolute standard, and then they dim again. So by finding these stars in nearby galaxies, we can calculate the distance from their apparent brightnesses. Again, fairly straightforward, nothing really fancy going on there, just a bunch of calculations and good observations. Distances to far galaxies. Here's where we start to get into theoretical problems. Back in the last century, Edwin Hubble discovered a relationship between the distance and the spectral redshift of nearby galaxies. And the resulting Hubble constant was then used to estimate distances to far galaxies having no resolvable stars. So calibrated on the nearby ones, whereby we know their distances fairly well, and then extrapolated beyond that. It's interesting that over time, the value of the Hubble constant has not been constant, that it keeps getting updated. It changes with new observations. And so the apparent age of the universe keeps changing accordingly. Okay, for redshifts, what's going on there is that there are certain absorption lines or emission lines in the spectrum of the light coming from a star or a galaxy. And we have like the ultraviolet here on the left and infrared on the right. If this is the spectrum that we'd find here on Earth, then on a faraway star, the spectrum is shifted towards the red end. And there's a certain mathematical relation on that redshift. Okay, the causes of the redshift, the ones that we know about, of course, are the Doppler shift and the speed of moving away or toward us. It operates like a Doppler radar that, or if police are using infrared radar system, it works the same way. Just measuring a Doppler shift,